All right, so we are back with section 5.6.3 today. We're going to cover a few examples that should allow you to get through the assignment tonight. So we'll start with this first one here, and what it says is express y in terms of x. If natural log of y equals 1/3 natural log of x plus natural log of 4. So first of all, what does express y in terms of x mean? Right. So you started studying this concept back in probably most of you probably in around 6th or 7th grade when you started studying algebra. But what this means, the way you should read this is basically when it says express y, that means solve this for y. You want y equals. And then in terms of x, well, on the other side of your equation should be an expression that contains the variable x. Right. So it's not that bad. You're going to treat this very similar to the equations you solved yesterday. The difference is yesterday you were solving equations for numerical values. In this case, you're essentially going to solve this for y, and you're going to have an expression on the other side, an algebraic expression on the other side of the equal sign instead of a numerical value when you solve it. So let's just jump right into it. First thing you want to do is you want to look, get a sense of the equation and look at, okay, so on the right side, we're going to need to condense those two natural log terms. In order to condense, you need to deal with this coefficient of 1/3 first. So we're going to use that power property, right? And we're going to rewrite it as natural log of x to the 1/3 here, right? At this point, you really can't do anything with x to the 1/3. I don't necessarily recommend you write it as a radical, a cubed root. I personally prefer to just stick with the 1/3 exponent. But now here we have the natural log x to the 1/3 plus natural log of 4. At this point, we can use that product property, and basically we're identifying that there's a sum there, which is going to produce product of x to the 1/3 and 4. So when I condense these two, I chose to write it as we write typical algebraic expressions where we put the coefficient 4 before the variable x to the 1/3 there. So at this point now we're sitting with natural log of y equals natural log of 4x to the 1/3 power. Solving for y. So we have a log equal to a log. And we can use that third property we discussed yesterday. Both these logarithmic terms are in the same base E. So if that's a true statement based on the equal sign, then we can just turn around and set the arguments equal to each other. Y equals 4x to the 1/3. Now, if you did choose to work with the radical, you could express it as y equals 4 times the cubed root of x. Both are correct. Both are simple. I would prefer the top highlighted answer as opposed to the radical here, but they're both correct. You'd get credit for both of them there. All right, so that's our first example. Let's jump to our second example. This one's a little bit more complicated. Right? This requires some critical thinking and game planning before you just jump into it. So what we're going to do is we're going to manipulate the given log expressions, so just focus on log base 6 of 40 first. Right? So our goal is to manipulate this and rewrite it so we have some kind of expression in terms of x and y. Right? Now, in the directions up here, it gives us two statements. Right? So it says log base 6 of 2 is equivalent to x. Log base 6 of 5 is equivalent to y. These are, think of them as hints, right? We want to use log base 6 of 2 and log base 6 of 5 to eventually decompose log base 6 of 40 and then eventually replace those deconstructed terms with x and y or some combination of x and y. The other thing I'm going to point out here is when you're tasked with doing this type of equation, you should always bring into the fact that you can introduce another logarithmic term that you don't think of very often that is very helpful. So the way you're going to do that is you're going to focus on the base of the given logarithms, right? It's in base 6. So you can work with any log base 6 statement where the argument is some power of 6, right? So for example, 6, 36, 216, right? Any power of 6 there. So one way to look at that is, you know for a fact that log base 6 of 6 is equal to 1. So if you needed to use a 6 in this situation, it's safe to use because you know the value of log base 6 of 1 without really using a calculator. You know, and this can continue, right? Log base 6 of 6 squared, which is really 36, right? We know that that is equal to 2, and so on, right? So these argument values, 6, 36, 216, can be helpful in some cases. You don't always need to use them. Now, to start the problem, we're really looking at log base 6 of 40 right now. So what I'm going to do is just going to advance to the next slide where I have some work already generated. So focus on the argument right now. It's 40, right? And you want to look for factors of 40 that you can use with 5, that's the argument right here, and 2, the argument here, and potentially 6, right? Between this is equal to 1, or 36 for that matter, right? So factors of 40, or it's a good way to start. Sometimes you want to just go right to the prime factorization of 40. So the first 2 factors I think of when I see 40, besides 40 and 1, are 5 and 8. It's just who I am. Some people will think of 2 and 20. It doesn't really matter. So 5 and 8 is helpful. Notice right here, this 5. So this is helpful because that means I can use this log expression, which is equal to y, to help with this problem. But there's no 8 anywhere, and I can't really make 8 with a 6 up here, and this is a 2, so that's not very helpful at first. So that's when, you know, instead of just looking at the factors, maybe look at the prime factorization of 40. So 8 is also 2 times 2 times 2, or 2 cubed. That is helpful because 2 cubed is 8, and the base 2 in this expression right here can be used with log base 6 of 2 in the argument there. That's going to be helpful for us, right? So now that we've kind of established a relationship between the given log expressions here and the argument right here, 40, or the factors of 40 for that matter, we can start now decomposing or expanding log base 6 of 40. And it's a little bit more difficult in this case because you don't actually see a product of 2 numbers as you did in the previous 2 lessons. So since 5 times 8 is 40, what I'm going to do is I'm going to basically rewrite this log expression, log base 6 of 40, and expand it into log base 6 of 5 plus log base 6 of 8, right? We know right now that this is equivalent to, space here, log base 6 of 40, okay? But again, this log base 6 of 8 right here, we don't have an 8 up here to work with, so that's why this expression here is more useful. So log base 6 of 8 is also log base 6 of 2 cubed. And then we can start using the power property here, where I can take this exponent 3 and rewrite it as a coefficient down here in the next line of my expression. So now we're dealing with log base 6 of 5 plus 3 times log base 6 of 2. This is ultimately where we needed to get to. Now that I have this, I can go back up and look at the values I have for log base 6 of 5 and log base 6 of 2 and incorporate that with my final answer down at the bottom. So log base 6 of 5 was given to us. It's equal to y. So I can replace log base 6 of 5 down here with y, and log base 6 of 2 is equal to x. So I can replace log base 6 of 2 with x down here, right? So this log expression is equivalent to x, this log expression is equivalent to y, and then I can just rewrite it as y plus 3x and be done with the problem. Now this expression is written in terms of y and x, right? So y plus 3x or 3x plus y, both are equivalent. Now there's other ways to go about this problem. There's not only one. So let's look at this, right? So, you know, let's say your first factors of 40 you thought about were 4 and 10, right? It's not a prime factorization. 10 is not in our original list, right? We only have 5 and 2 right here. And remember, we can still use 6 from, that one we introduced because we know the value of log base 6 of 6. But, we just, let's say we viewed it as 2 times or 4 times 10, right? Neither one of those are helpful until then we start factoring 4 and 10 independently. So 4 is 2 squared. 10 is 5 times 2, right? So there you see that, you see 2 showing up here, you see a 2 showing up here, and then you also see a 5 showing up right here, which is helpful. So at this point, what I can turn around and say is I can then now decompose log base 6 of 40 into log base 6 of 2 squared, which is 4, plus log base 6 of 5, plus log base 6 of 2, right? So remember, this piece right here is the same as log base 6 of 10, right? Which is translating to this factor. And this piece right here is log base 6 of 4, which is translating to this factor right there. And then at this point, that first term here, I have to use my power property, bring it out front. So that's going to give me 2 times log base 6 of 2. Remember, log base 6 of 2 from above is equivalent to x. So this first log expression here becomes equivalent to 2 times x. 2 from the exponent, which is written out here as a coefficient, log base 6 of 2, which becomes your x. And then at this point, log base 6 of 5, this first expression here, that is equivalent to y from above, and log base 6 of 2 from above is also equivalent to x, right? So now I have 2x plus y plus x. I can combine that into 3x plus y, or even y plus 3x. The order in which you leave this one doesn't necessarily matter. And, that's the first example in this case. Second example is a little bit trickier. So when you focus on the argument 3 right now, 3 is not listed for us whatsoever. We have a 5, we have a 2, not very helpful. There's no factors. 3 is prime, so you can't really look at it as factors. And this is where you have to kind of stretch your thinking a little bit. In fact, this is where powers of 6 come into play, right? So log base 6 of 6 is equivalent to 1. 6 is not a factor of 3, but it's definitely a multiple of 3, right? So product property, which is what we were working on in section A, is easier because you're looking at factors of the original argument. However, we can use the quotient property, right? Remember, when we subtract logarithms, as you can see right here before I explain it, right? Subtraction of logarithms is also a quotient or a division or a fraction, right? So sometimes what you want to do is look at the original argument 3 right here, and then look at multiples of 3, right? So the next multiple of 3 is 6. So I can actually look at, okay, well, can I use 6 to my advantage here, right? So, this argument 3 times 2 is 6. I do know the value of log base 6 of 6. It's equivalent to 1. So then I can kind of look at the argument as 3 right here is equal to 6 divided by 2. So at that point, now that's where we're going to use the quotient property, right? So this quotient, this division, this fraction right here is going to indicate a subtraction for us. When we go to decompose, or excuse me, not decompose, expand, it's a better word to say, log base 6 of 3. So this is going to be expanded into log base 6 of 6 minus log base 6 of 2. Log base 6 of 6 is 1. All right, this was not given in our original list here, but we can introduce it because we know log base 6 of 6 is equivalent to 1. We also know log base 6 of 36 is equivalent to 2, and so on. And then at this point, I'm going to replace log base 6 of 6 with 1. I'm going to replace log base 6 of 2 with x. My final answer here is 1 minus x. And that's pretty much it, right? So there's going to be some manipulation here. You're going to have to work with exponent properties, logarithmic properties, and then ultimately express the original statement here in terms of, the logarithms or variables those logarithms were assigned to in the original part of the problem.